So welcome to the GraphGeeks, one of the GraphGeeks' first official training, Graph Tech Demystified, if I can speak this morning. I'm Amy Hodler, host. We're here with Paco Nathan, also known as the evil mad scientist, also one of the evangelists and leads at Sensing. Paco's been in the industry for decades. He has a long history in both graph, AI, machine learning. As many of you already know, Paco, probably understand that he has a unique talent for making the difficult topics more understandable. So it's why I asked him to participate in this longer training.
We're going to cover core graph concepts, real world applications. We'll look at industry use cases and practical examples, common pitfalls to avoid, and really where are some of the limitations about using these kinds of approaches. And definitely go a lot into graph analytics. Because I think that this right now is where a lot of the power is. And then in the next section, we're going to go level up a bit, talk about more sophisticated kinds of approaches with graph technologies, looking at patterns and motifs, looking at graph neural networks, what's going on with reinforcement learning, which I think is hugely underserved at the moment. Certainly looking at GraphRag and AI agents, agentic workflows and memory, but then also, outlook way beyond this. And just to kind of give a preface about this too, I think that when you look in the graph space, certainly, there are some very well-known vendors of graph databases, but when you really look at the technologies, there's a lot of different camps, and I'll point it out coming up, but there's like, 6 or 7 different camps where the main people go to different conferences. They don't really talk to each other. There's not a lot of integration between the different types of strategies, and really all that's in common is it's about graphs. However, when I look at what gets used in industry for real world applications, industry use cases, typically, you're leveraging 2 or 3 or more of these different areas, the different camps. And you're having to find ways to build out integrations. So I really want to focus on that there's a breadth of a lot of different kinds of approaches. And usually when you're in a real world app at scale in production, you're not just set in one thing. You're not just using the graph database and graph queries in that graph database. You're probably also mixing and matching with some, like some visualization, interactive visualization with some graph algorithms, maybe some areas of using machine learning models, GraphML, LLMs, etc. So about stitching all the pieces together, but before that even, recognizing that there's a lot of different pieces. That's really what this talk is about. So I love this quote here from Abhishek Nagaraj out of UC Berkeley. Think of data as an imperfect map of the underlying entities. And there's more of a talk there. I'll just point to it. But I love this notion of an imperfect map. And we'll come back to that. I think that in itself can be leveraged, not just conceptually, but we'll look at Kinaviz and some things from Weidong Yang and team, how they've really acted on some of this a little bit later. But we could say that any collection of data sets that you want to work with is an imperfect map. And when you start to merge those data sets together, what you get are the underlying entities that are being represented, probably in some kind of class hierarchy. And so those will become nodes in a graph. And then you've also got semantics of the connections between the entities that are being represented. Those will become relations in a graph. And you probably have annotations for all the above. Might be like, where did this come from? Why does it matter? What's the real relationship between these 2 entities? Is it, an owner and a company? Is it a parent and a child? You've got all kinds of annotations. These become the semantics that are applied, and also other data that's basically represented as annotations. So those are properties. And so what I'm saying is if you take a bunch of data sets, and typically any real world application I've ever seen has multiple data sources. So you take a bunch of data sets, you put them together, you come up with this imperfect map, and the results are you get nodes, relations, and properties. You have the elements to build a graph. Now, identifying the real non-obvious connections and structuring it well with structuring intent about how you manage knowledge. That's a harder problem. We'll talk about that in a bit. But at the end of the day, I believe a lot of this is about building and navigating and leveraging graphs. Graph technologies are about representation. This has been one of the core areas in artificial intelligence for at least the past 5 decades. Established AI practices from earlier decades, they're now being reasserted in contemporary work. And a large part of that includes where graphs fit in and where graph-based inference fits in. And a key thing to understand, at least from my perspectives, are that AI is a practice. It's not a thing. You can't point to some black box and say, well, that is AI. I'm not going to be any part of any discussion like that. AI is a practice. There are many different areas. There are many different types of technologies employed. And typically, when you're talking about a practice like this, what I mean is it's a matter of groups of people and machines collaborating to come up with capabilities beyond what an individual would be able to do. I know there's a lot of discussion about LLMs right now. LLMs are not the end-all, be-all of AI. It's merely one component, and I just really want to back off on that. So please do not ask me, why aren't you just using an LLM to do all this instead? Because that is not what we're talking about here. We're going to talk about AI as a practice. Graph data structures. Okay, you can find graph data structures throughout computing. If you dig into the internals of the Linux operating system, you will find a lot of instances of using graphs in really critical ways that are relatively arcane, and they're not exactly what we're talking about when we talk about, say, graph databases. But also, if you look at how SQL queries run, how SQL queries are planned and optimized these graphs, you look at security systems. Definitely, there's multiple graphs being considered in terms of like entitlements and threat graph and network graph and all that. You look at how spreadsheets work. Spreadsheets are graphs, period. They have a user interface, which is table format, but everything going on in the calculation of spreadsheets is based on graphs, and so on. So there's a lot of flexibility of using graphs to represent data, and I find that it may actually be kind of deceiving. It makes graphs look easy because they're everywhere. But I think that for a lot of people coming into this field, there is this notion of, gosh, if we're using graphs, maybe we can just use one big graph to represent all the data in our organization. And I guess technically, yes, that could be done, although I think it's a very bad idea in practice for several important reasons. And also, I just never see it work. So I want to give some caveats that even though graphs are kind of ubiquitous as a computer science data structure, we're talking about graph technologies here used a lot for work in data analytics and machine learning and leading into AI applications. So that kind of constrains the definition of what are we talking about in terms of a graph. Also, I want to be very careful not to suggest that we just use a graph for everything, because that's also a bad idea. And knowledge graphs don't necessarily perform magic and solve all complex problems. They are good at representing data which can be manipulated in ways that are more effective and closer to business needs at scale, much more so than, say, possible with a purely relational approach. Managing data in a relational data lake, that's probably what your company is doing, and that works out well as far as data management practices, data engineering and all. But when you actually need to navigate the data, you need to pull it together, and typically that's where you start to leverage the connections in it. And that's why I say graphs are probably better at representing problems like supply network optimization or value chain or network security threat identification, on and on and on. There's a lot of places where once you actually start to use the data, you want it in a graph. And I'd like to point out to a couple of papers done by a couple of sets of friends. Actually, I think they were all kind of working together on this. But Claudio Gutierrez and Juan Sequeira, also Aidan Hogan, and a whole string of other authors that I don't have enough room on the page to cite. But here's a couple of really good papers that are survey papers out of the early 2020s, really talking about knowledge graph and what does this mean. And I still think that these are kind of the canonical survey papers for right now. I also want to be careful while we're talking about caveats and practices. You may have heard the term graph theory from mathematics. And I find that, people who are, how should we say, more on the business side of the house, but maybe not on the technical side of the house, when they want to start talking about something that is complicated and a lot of technology and maybe a little bit more academic, they'll rush to say something like graph theory, even though they probably don't have a good idea of what graph theory is. Graph theory is actually fairly specialized. And a lot of the mathematics that are in graph theory, to some extent, they are purposely simplified. One might say overly simplified. They don't really apply for a lot of the kind of industrial problems that we're talking about. A lot of the theory, well, it might inform certain parts, but it doesn't really translate into contemporary business applications. But there are other disciplines that are, even more academic, if you will, that are within the scope of graph technology. So we're not really going to talk about graph theory. Just, I would say, avoid that as part of your lexicon. But really take a look at some of these other areas where there is a lot of work going on. Again, it's kind of in pockets, in different camps. I've got an illustration here where I'm showing, in the top left, there's a lot of work on, say, axiomatic approaches, and what can you do with formal reasoning on top of a knowledge graph. And if you look at a W3C stack, there's a lot of that kind of work. But then over on the top right, we've got probabilistic graphs, and we can talk about statistical and relational learning, and there's an enormous field there. And then somewhere in the middle, I've got graph algorithms. This is another area really interesting. That one is probably closer to a lot of more the formal graph theory, but not necessarily. But then you've got query languages, Cypher and Sparkle and all kinds of things, and they're not exactly what these other parts are all about. But then there are things we can do just by basically doing traversals and really looking, across a graph at scale. There are some types of systems that leverage more of the traversal, especially if you're doing any sort of bulk processing of very, very large scale graphs. So that's kind of a different camp. There's definitely the people doing graph neural networks, which had been very academic for a while, but we're actually seeing really good revenue-bearing use cases at scale at LinkedIn, Spotify, and others. And that's really coming up, I think. And then there's also just the camp of visualizations, and that's an enormous area, a lot of diversity. I find that most of the vendors in the visualization space kind of cater to particular areas, so it's even hard to compare them. But I really want to point this out. I tried to plot this out in terms of like formalism versus like robustness. Some of these areas are really, really formal. Others are, well, let's just say they can deal with a lot of really messy data, and they maybe aren't quite as formally defined. We'll cover that. But the problem that we've seen over the years is that these camps really don't go to the same conferences. They don't really talk much with each other, and neither does their software. And that kind of disconnect is a major hurdle if you're working in production in industry. Efforts to bridge between these disciplines are producing more sophisticated forms of graph inference, more hybrid approaches, especially when you get into AI applications that are downstream from graph work. And we are seeing emergence of very interesting work that I think you would probably put a label on it as neurosymbolic, kind of a nice umbrella for a lot of the hybrid work, but there's different areas of hybrid work. And there's even some others that I don't have represented in this, like for instance, I should put high dimensional computing somewhere on this graph. And maybe there's actually a couple of areas where that would probably fit. But at least we're trying to say there's multiple disciplines. And so let's dig into this a bit. Now, when I'm talking about axiomatic inference, a lot of this is going to be coming out of, you'll hear about RDF, you'll hear about the W3C semantic web stack, you'll probably hear about things like OWL and Shackle and other types of technologies that are built on top of RDF. RDF has a very interesting provenance because, talking with Oralasa, who created RDF, he wasn't really working with graphs. What he was working with was representation languages from AI. And Tim Berners-Lee was talking with him and pointed at him and said, you have this idea, go follow it. And they built out RDF as a way of representing ways that agents could crawl web pages across the World Wide Web and be able to get metadata about those web pages or get some kind of data in a formal representation that was embedded inside of web pages. And from that perspective, RDF has been an enormous success because currently 40% of all web pages in the world have some RDF in them. A lot of that, of course, has been driven because Google has told people for SEO reasons, you want to put some schema.org in your web page. And that's what it was intended for, and that's what it does. The paper on this, we'll point to Natasha Noy and Deborah McGinnis, a couple of good friends, a couple of dear friends, and they were at Stanford back in the early aughts, late 90s and early aughts, and they wrote this paper called Ontology Development 101, and that's just the foundational cornerstone of ontology work and really, some of the early expression of where we're going with axiomatic inference. There's another one, again, I'll point out about Eden Hogan, Stefan Ducker, talking more recently about OWL and what's going on with reasoning systems. I think that this area is really important because there's been so much work over the decades that's been built out on how to do reasoning, how to really leverage symbolic aspects of AI and do really intense reasoning systems. And to some extent, I think in the current dialogue that's very focused on LLMs, you're kind of throwing the baby out with the bathwater because there's so much talk about inference and about reasoning without any retrospective, it seems, very little citation or reference to all the work that's been done before. And all that work is actually in production and available to use. So again, I think that this is an area to really lean on for some paths forward in AI. When I talk about query languages, another area here, there is an emerging standard, more than emerging, it actually is a standard, GQL, which takes and pulls together some of the other historically popular query languages, such as Cypher and Sparkle, and puts them into a standard that's probably more recognizable in many ways. It's beginning to be adopted. I don't think that it's pervasively adopted. I don't think that would be a good way to say it yet. I think if you want to see some critiques and you want to hear some counterexamples, I definitely would recommend this paper from Google, Jesse Weaver and company, who did Introducing Path Query. I think they do a pretty good analysis, as well as making the case for why Google doesn't go in those directions, even though Google does a lot of graph work internally. They've really taken a different approach, and they have different constraints on their query language. And to me, from my experience, the kind of constraints that they put on path query actually really make sense. If you've ever had the task of implementing a Cypher query engine and doing optimization on Cypher queries, you'll probably know what I'm talking about. But I want to point out something, that when you look across these different query languages operating on graphs, I mean, I have some mathematics background way back when, and from, a perspective of more, say, like abstract algebra and what we see in functional programming, you might hear people talk about closures. If you're familiar with Apache Spark and Databricks, it's all based on using closures. One of my problems with this is that when you look at how graph queries work, you apply a graph query to a graph, and as a result, you get a table. And I've always found that to be an enormous disconnect. There are some systems that don't. If you look at what Google is doing with Spanner Graph and BigQuery being adapted for exporting graphs as like data marts, it's a service that I've heard it called Google Big Graph. It's not really public release yet, but there's been some talks about it from Bailey and others. If you look at what Google's doing, also, maybe look at what Oracle Graph products with AI 23 and later releases. They actually produce graphs as a result of running a graph query. And, to be fair, when you run a technology like Shackle and apply that, it's not a formal query language, it's a constraint shape language. But when you apply Shackle to a graph, you also get a graph of counterexamples as a result. So query languages, I think there's some great stuff there. GQL is very promising. I think there's some excellent criticisms that are important to pay attention to. And the Google paper from Weaver et al. is really good for that. I think that this notion of graphs are important, therefore, whenever we run a graph query, we produce tables. I've always found that to be absurd, but Oracle and Google are showing a different approach. What I will say is that one of the dirty little secrets in the industry is that there's a lot of emphasis on graph queries, and also, frankly, behind closed doors, graph queries enhance vendor lock-in. And if you listen carefully, usually the industry vendors for graph databases are really big on pushing, let's just do everything in the graph query language. And I'll let you figure out why they do that. Okay. One of my favorites out of all this is graph algorithms. And there's a very sophisticated space here. And to be candid, definitely given the kind of work I do and who we do that work with, I have to be careful. I can't disclose a lot of things, but let's just say that some of the largest production graph technology work that I see going on right now, all day, every day, really they use graph algorithms. And in fact, in some of the really big ones, they don't even have a graph database. They do write-behinds, but they're using GPU clusters to run really large graph algorithmic work at very blindingly fast speeds, typically based on something like cuGraph. And so there's Bradley Rees and team at NVIDIA. They have an accelerated version of Network X. If you program in Python and you work with graphs, you probably run across Network X. It's basically the go-to space for so many interesting graph algorithms being implemented. And it's kind of a lot of glue, if you will. And increasingly, when you look at even graph databases like Kuzu, they integrate very closely with Network X, which I think has been a very brilliant tact. Here's the original paper from Hegbert and company introducing Network X back in 2008. I find out in business use cases, what is usually needed by the business use case, if we just stop talking about vendor selection prematurely and really focus on the business use case, at the end of the day, it's usually graph algorithms. There's something that needs to be done to manipulate the graphs and pare down a very, very large amount of data into something that's workable, something that is at human scale that people can make business decisions about, and typically use graph algorithms to get there. Okay, another area not quite as popular, I would say, but increasingly, and arguably also one of my favorite areas in this, is probabilistic graphs. So there is a large space that's called statistical relational learning. One of the best authors in that space is Lisa Couture out of UC Santa Cruz. And this covers a lot. You've probably heard of Bayesian nets, using Bayesian approaches in networks to be able to calculate conditional probabilities and propagate them through a graph. That's an example. There's Markov networks. There's all kinds of things going on over in that space of probabilistic graphs. When you really dig into it and try to use this kind of technology in production, one of the things you do find is that some of these things are computationally intense. I mean, like order cubed kind of intensity, which means that you put 1 million elements into a graph. I'll just let you calculate what 1 million cubed is. So, I mean, I think there's a lot of academic work in this area, and a lot of it just doesn't seem to work in production. But I highly recommend this team. Came out of Maryland, but is now at UC Santa Cruz. Lisa Couture leads it. They have something called Probabilistic soft logic. They've done some very interesting, again, optimization work to make this at least fit with conical optimization so that it doesn't grow unbounded. So it's computationally efficient. And probabilistic soft logic, will come back to this, but it's one of the most interesting areas that I see of leveraging this area of statistical relational learning. The other big thing in statistical relational learning is causal. And there's been a lot of work in causal graphs. I'll point to some stuff here, but also later in terms of out of USC Viterbi, led by Urvashi Mitra. What they've been doing a lot with causal graphs there, which I think is really, really exciting. One of the most promising current areas of emerging work in graph technologies. And let's shift over completely. We'll talk about graph neural networks. And this is something that's typically called graph representational learning. There's an excellent book. William Hamilton was a graduate student at Stanford out of Yuri Leskivec, who had really led a lot of innovation there. Hamilton put together a book. It's allegedly published by Morgan and Claypool. I actually haven't seen it published, but the full text is there on his website. And it's a really great text. It's called Graph Representation Learning. Hamilton had worked on an algorithm called GraphSage, which is one of the more popular approaches doing graph neural networks. And so let's break this down. If you've got a neural network, and for what it's worth, my lab partner when I was back at IBM Research as a grad student back in the 80s, working on an AI project, my lab partner would not stop talking about neural networks. She loved it. She actually eventually became a neural physiologist. And anyway, but she just kept talking about neural networks. And so we were locked in a small room day after day. And I was like, Janet, I promise I'll study neural networks. And I did. And I've worked in neural networks since the mid 80s. I was CTO for a company doing neural network hardware accelerators back in the 90s. I got to be on a team led by John Hopfield when I was at Bell Labs. He later got a Nobel Prize, or shared a Nobel Prize in this area. Long story short, neural networks. I love neural networks. Neural networks are structured such that you have a vector of input, and then you have a vector of output, and you have some hidden nodes in between. It's a network. But the in and out is a vector. And when you have layers of neural networks, you have these vectors moving across, maybe with autoencoders or however, but you've basically got vector in, vector out at some point. If you have a graph, it doesn't really fit a vector all that well because graphs are geometric, or maybe you could say topological. Graphs have shapes to them. They have connections. They don't all fit into a linear vector very easily. But there's been a lot of sophisticated work, and so graph neural networks are, the basic idea is, can I start with a node and then look at the neighborhood around that node and grab as much information describing that context, stuff it into a vector. And then I can train a neural network that if it sees a lot of this pattern, it will predict that node and its context. Or I could look at an edge in a graph, and I can do the same thing. Let's look at the neighborhood of that edge, and again, train for that vector and then be able to predict that vector in its context. Or I could just take a subgraph, a small part of the graph, and essentially take all the neighbors there and again, look at their information, fit it into a vector, train a neural network. And this is an area that, frankly, in the early 2020s, if you want to get a paper published about machine learning, you had to use these magic letters, G and N. And then I think in 2023, if I recall the story right, Neo4j commissioned an industry study to say, hey, where's this all being used in production? There must be some really interesting production use cases. And they came back with crickets. Even Meta, which had been one of the main places really pushing this, they said to the industry analysts, they said, we pulled the plug on that stuff. And then you find out a year later, LinkedIn and Spotify both published their production use cases, which had been in production for a couple of years. So effectively, they couldn't spill the beans when this Neo4j sponsored industry analysis paper was going on. Basically, the major players in this area couldn't talk about it. So effectively, they didn't answer. But 2024 and since, we've seen a rise of production use cases for graph neural networks. And I think that this is really important. It's a way of augmenting. I think some of the most fascinating areas for graph neural networks are in pharma and drug retargeting. Frankly, that technology was used for pharmaceuticals that went into COVID treatments during the pandemic. We'll have some talks about that later. But it's lesson learned. When a new kind of technology comes out, it usually takes a few years before the right data sets are available to actually illustrate that technology. It takes a few more years before industry can hire up the experts to put something in production. It takes a couple of years before that will go in production. And frankly, if you're a pharma, you're not allowed to talk about anything until 2 years or later. And if you're in social media, probably even longer. So it takes years before HR will let you even talk about what you're working on. So if you do the math, a new technology will come out in the graph space. It might be 10 years before anybody's willing to admit that it's being used in production. That's a problem. And for graph neural networks, that actually, fortunately, it was only more a matter of, I think, about 7 years from the introduction of talking about geometric representation and in PyTorch and whatnot, and then from there to having actual reported use cases. Okay, visualizations. There's a lot going on in the visualization space, and they really do work in some different areas. The vendors tend to focus on specific business verticals. Interactive visualizations are really important because, if you have hundreds of millions of nodes in a graph, you might be able to visualize a really pretty picture, and the executives might print that and frame it and put it on the wall, but it doesn't really do anything else. I mean, there are some use cases for using really large scale visualization, certainly in cyber threat, in cybersecurity. But generally speaking, you want to be able to get down to a scale where you can manipulate. Like if you're at a fraud team at a bank, you're not going to look at 5 billion nodes when you're going through your case management tool. A suspected fraud case comes up, you want to look at 20 nodes, and you want to be able to interact with it and drill down and dig up other information. So interactive is really the important part of visualization for a lot of these use cases. I've been doing work lately with YWorks a lot, with some of the integrations in Kuzu. Really, really fantastic work for embedded graph visualizations like in Jupyter Notebooks. Ogma comes out of the folks that do Lincurious. Also really interesting work. That team had started with graph visualization with something called Gephi way back when. I used to use Gephi a lot. There's JavaScript libraries that are popular like BizJS, D3JS, and there's Python wrappers like PyViz. I use that a lot, frankly. There are some great vendors. Kinaviz we work with, highly recommended. Cambridge Intelligence has a really incredible suite of different graph visualization. Tom Sawyer we also work with, really amazing work there. Like if you go into a skyscraper in Manhattan or London or wherever, there's a lot of graphs in that building. Like for instance, when you look at the network for routing HVAC, or for routing electrical, or for fire suppression. And all these things are, really important, because if you're in a skyscraper, fire suppression is a really important thing. And so there's a lot of compliance, there's a lot of inspections, a lot of audit, and being able to manipulate those graphs in the enormity of different graphs in one skyscraper is kind of mind-boggling. Tom Sawyer does really, really amazing work. That's for instance, they do a lot of different kind of work, but that's one area there. And there's others in this space. Definitely, check out what Esri is doing with graph visualizations, along with geospatial analysis. But again, the different the different vendors tend to focus on specific verticals. So visualizations are really important. Also, kind of difficult to integrate, but it's getting better. And actually, some of the best integration that I've seen for for graph visualization. In the middle of this slide here, I'm pointing to something called G.V, Arthur Bijard and crew. And I think that, they've focused a lot on being able to have procedural traversals, but also integrate across a lot of different graph platforms and query languages, but also be able to do, really accessible, easy ways to get started building graph visualizations that are sophisticated and run at scale and run fast. G.V, I think, is really kind of pulling that off. But more to the point here, I want to talk about procedural traversals. There is a query language called Gremlin that comes out of Apache Tinkerpop. And whereas most of the query languages you'll run into, SQL being for instance, most of the query languages tend to be declarative. You sort of describe what you want to have happen or have happened, and then the query engine will make that happen. And the trouble is that you can't get in and programmatically go after something in the graph. You have to bang your head against the wall to figure out, how do I describe this declaratively? So, there's good and bad about using declarative query languages. And most people in the data space are trained to think in terms of SQL and SQL only. Let's just say that there are other ways to query data management tools. Gremlin is kind of stands out from the crowd there because they provide programmatic access to graphs where you can write some code and you can have that code go through your software engineering process and have unit tests and do things like you want to with software. I really like this team. There's a lot of really amazing people that came out of the Tinkerpop project over the years. I used to teach graph courses with one of the former leaders of this team. Anyway, a lot of good stuff in terms of procedural traversals. It does fit into some of the more interesting areas of axiomatic work with graphs. I think that Prometheus AI and Adriano Vlad and company, they're doing really interesting work on traversals meets axiomatic work with something called Vatalog, a variant of Datalog. And this is part of what can really tie together the other disciplines. I think it's a really interesting space to watch closely. And certainly that's the premise of what Arturo and company are doing with G.V. So if you're interested in industry applications, production at scale, how do we integrate across these different camps that don't appear to really talk with each other much? These are the people who are doing that. And definitely watch this space. I'm looking at time. Okay, we've got another 10, 15 minutes on this section, so I think we're doing pretty well. I want to say something, and I want to highlight it more than anything else I say, that when you're working with connected data, when you're working with graphs and graph technologies, regardless of what anybody else says, relations are much more important than entities. The relations in the graph are the important thing. And this is what really distinguishes graph work from relational database management. Even though there's the name relation in relational database management, at the end of the day, most of the practices are about facts and fact tables and schemas that are relatively fixed. And the relations represented in SQL are, they're kind of watered down intentionally. That was actually back in the day, IBM had graph database technology, and in the 70s, and there was a team out of San Jose being led by Edgar Codd and William Kent and others. They did fantastic work on data management back in the 70s. IBM did some user testing. Actually, I worked for somebody who was in the room when the decisions were made, a former IBM exec. Used to work for Jack Olson. Anyway, long story short, IBM had really good graph technology back in the 70s. They were thinking about commercializing it as a database platform. They did some user testing, and they came to the realization that working with graphs requires some chops, and that if they dumbed it down, they could get a broader market. And that's when they took what Codd and company had been working on and kind of destroyed it and started calling it SQL. So they put guardrails in to be able to have a broader market. And the guardrails are basically a lot of what you see out of SQL now. And a lot of that was really watering down the relations. And the people at the time knew that working with connected data, even if you look at Codd's original paper on relational data and projections, tables, whatnot, you see that relations are more important than the actual facts. That was thrown out the window. So I really want to underscore here that we've had norms inherited from decades of having relational data management beaten in everybody's skulls, that you're supposed to focus on tables of facts and use joins to reconstitute. And you know what? The relations aren't that important. Bullshit. It's a very Cartesian, Aristotelian view of data. It was originally intended for financial reporting. The original SQL work was done on behalf of the US intelligence community. That's why the name Oracle came out. But then it was sold commercially right after that to bank executives, because at the time, the data management tools they had in banking had non-deterministic runtimes. And if you're a bank VP and you have reporting to send out to the IRS, you want to know that you're going to get those jobs completed in time, or you're going to lose your bonus. And in case you're not aware, if you work in finance, if you're at a vice president level, like vice president of IT in finance, they typically make seven-figure bonuses, a lot of them at the larger banks. They do not want to lose their bonus because somebody screws up reporting. And so when Oracle and others came in and said, hey, look, we can give you predictable times and show you how much compute you need to buy so that you make your reporting deadlines, the banks just all gobbled that up. And that's where relational data management really got its push. But representing relations is important. And I'm going to point out a few times a series of articles called Knowledge Architecture. It's by Mike Dillinger. If you know the history, Mike Dillinger comes from really more of a linguistics background. He was hired to formalize graph practices at eBay, and then went over to LinkedIn, spent years formalizing graph practices at LinkedIn. It's a really hard problem. He has an excellent discussion about this called Making Knowledge Graph Relations First-Class Citizens. And I love everything that Mike publishes. So look to him to talk more about this. Consider this. If you're a risk analyst and you're having to track down some forensic accounting, you've got thousands of money transfer transactions at the bank, typically you're looking at it like the left-hand side of the screen. You're seeing a table, and your mind is becoming scrambled because professionals working on behalf of, I don't know, the Kremlin, have been hijacking a bank in Estonia, which is a branch of Danske Bank. And for a period of several years during the 2010s, they pushed $200 billion of money laundering across this one bank branch. And the Russian central bank actually even did test balloons twice to Europe and US and said, hey, we think there's some fraud risk going on in this bank branch. What do you think? And at the time, because of the financial crisis, the global financial meltdown from 2009, US and Europe said, yeah, whatever, we've got bigger fish to fry. So the Russians were like, cool. And then they just pumped $200 billion worth of money laundering through this one bank branch. And there's a lot more written about it if you want to read about the Russian laundromat and the Azerbaijani laundromat and others. But if you're the fraud analyst who has to go in and try to make sense, and professionals have been scrambling the data and hiding behind different kinds of tradecraft so that you couldn't discover their fraud, and there's $200 billion worth of fraud in there, well, guess what? Looking at a graph on the right side is going to let you do your job a lot quicker than trying to go after thousands and thousands of transactions in a table. Just saying. Okay, let me cut over to graph analytics real quick.
Paco, before you do that, I think it would be a great pause point on at least one question about knowledge graphs. So they weren't in your multiple disciplines, which I think, depending on how you think about knowledge graphs, that makes sense. But if you could maybe quickly define a knowledge graph for the group on the call, and then a question from Vikesh on if you have any thoughts on decentralized knowledge graphs based on what Origin Trail has done.
Yeah, great, great. Okay, so these are excellent questions. The first one, what is a knowledge graph? I mean, I pointed to some papers, a couple of friends, Claudio Gutierrez and Juan Sequeira, I think did a really excellent paper surveying that. Also, some of their colleagues, led by Aidan Hogan, came out of a workshop at Dagstool. I went to a subsequent workshop with that crew. They had a couple of really good papers to define. And so in some of my earlier slides, there's a couple of good papers that really go into definitions. The definition for a knowledge graph formally is kind of slippery. I can't really point to one thing and say, well, that's a knowledge graph and everything else isn't. But in general, you've got some connected data. You've got it represented as nodes and edges, probably as properties as well. You have some semantics applied such that what is represented in there can be interpreted by people coming from different domains, different disciplines. Like, for instance, if you're in a business, I guarantee if you go to the vice president who's in charge of sales, and then you go to the vice president in charge of procurement, and you go to the vice president in charge of marketing, and you ask them to define what a customer is, I guarantee they'll give you a different definition. And more to the point, the definitions will be conflicting. And when you look at their reporting systems, they actually use different reporting. So trying to understand what is a thing, what does that mean across different teams, even within one company, it's a really hard problem across different domains. And so part of the thing about a knowledge graph is, can we agree on some consistent shared definitions, some semantics, so that we can connect up the data, but also understand the meaning of it and how to interpret it, how to use it downstream. That's what I'm going to go with as far as a knowledge graph definition. Arguably, kind of slippery. It's more of a practice area than it is probably a thing as a specific technology. The second question about decentralized, yeah, I mean, the Origin Trail people are really interesting. I've been to a lot of their talks, KGC and other places. And I mean, Origin Trail is kind of looking more at what I would say like distributed ledger approaches meets knowledge graph, and using that definition for decentralized, which is really interesting. And there's some great use cases for it. Really interesting people. I think that decentralization about graph practices, though, is a larger topic, and that goes back to what we're talking about, domains. And so trying to have one graph, one enterprise graph that covers everything within inside of your organization, I don't think it's going to happen. Partly because it's so hard to get shared definitions across everybody. And whenever executives try from the top down to impose shared definitions that are exact, usually it falls apart. And generally speaking, the salespeople will revolt and have their own definitions. So what I see as a better practice typically is where there are different graphs in different domains that is distributed, maybe not formally decentralized, but distributed. And understanding across domain how to go out and take a look at more, say, federated approaches makes a lot of sense. And that's really the thing that works. I think that Zhamak Dehghani and others have spoken a lot about that. So that's how I would kind of answer about decentralized graphs, although I do think the Origin Trail people are really interesting. Are there other questions about that?
I think that would be good so that we have time to hit the analytics before the break.
Okay, cool. Thank you. Thanks, Amy. Definitions. In terms of graph analytics, again, this is a space where I think that there's a lot going on here with contemporary applications. So, for instance, if you've been watching Gartner research, usually up until about 4 years ago, Gartner research had usually kind of not been all that positive about graph work. And then I think it was in early 2021, they did this about face, and they're like, graphs are foundational. You must have it for data management. There's all these applications. So anyway, they kind of did an about face. And over the past year, I've been speaking at some different Gartner conferences and kind of getting coached by the Gartner analysts. And one of the things that they really underscored as advice to the speakers was, hey, look, we know everybody wants to talk about GraphRag and AI. We really want to talk about graph analytics, because we really see that right now what's needed in the marketplace with a lot of enterprise companies are for them to build out their graph analytics capabilities. And I agree. And so I've got some definitions here. I will talk about nodes and edges and properties. We talked about that. Subgraphs I've mentioned before, but basically anytime you have a subset, you're talking about a subgraph. That's really important because usually with a very large graph, you want to partition it into pieces that are, for instance, one particular fraud network and something that might go through a case management tool. That'll be a subgraph. Network motif it really comes more out of life sciences, but it's useful in other areas like in manufacturing. So a network motif is basically a pattern, a subgraph as a pattern. And there are different topological properties. We can look at isomorphic similarity. There's a lot of things there, but basically, can we recognize patterns within the graph that are repeated and maybe start to treat those as, think of them as like data objects if you've worked in data engineering. A path is basically the sequence of connections from one node to another, all the edges you traverse. You might hear people talk about multi-hop, but the pathing is really interesting because you can learn a lot about what's going on. Like, for instance, in terms of fraud, who's orchestrating a fraud network? Is it the ultimate beneficial owner? How can you leverage the paths from that UBO once you've identified them out to all the shell companies they're manipulating? Traversal is a process of visiting nodes and edges through some means, some structured approach by following the paths. You'll also hear the term algebraic object. So in algebra, we talk about sort of the bridge between algebra and geometry and going into graph theory. So if you have one dimension, you've got a point. If you have two dimensions, you have a line or a vector. If you have, sorry, take this back. If you've got 0 dimensions, you've got a point. If you've got 1 dimension, you've got a vector. If you've got 2 dimensions, you've got a matrix. And then beyond that, if you have multiple dimensions, you've got tensors. If you have some representation like time-based circulation among them, there are things like circulants and other types of algebraic objects that are multidimensional that get really complex. But basically, these are a way that we can talk about a bridge between what can we do on a graph using linear algebra or geometry. How can we bridge across that? And oftentimes it's by representing a graph as either a matrix or a tensor. And if you look at what's going on with neural networks, deep learning, you'll probably hear things like, oh, I don't know, TensorFlow or PyTorch talking about tensors, because that's a really good way of representing a network. We'll also talk about state machines. There are stateful transitions within graphs, and this is important to understand that there are time-dependent things happening, and the state of the graph changes over time. We'll go into a little bit of that. And let me just kind of close up. I know we'd like to take a break. We're close to that time, but graph analytics is usually a combination of a few things. Usually you're doing some kind of measures across the graph that we can calculate, and that'll give us a lot of insight about what's really going on there, and also indicate what kind of analysis would work later on. There's also graph algorithms we'll be running, and typically investigations with some type of interactive visualizations. You might hear this talked about as network science. That's another way, but think about it overall as like having a camera and focusing the lens. You've got a big graph, but you want to focus on a particular part for a particular reason. We can leverage the graph measures and the graph algorithms to focus that lens on the part that's important for what you need.